Haley indicated, I'm going to talk about climate scenarios developed from regional climate models, and really the subtitle is really the topic. It's like, do we end up with more uncertainty from using embedded models, or do we get better information, or both? And so that's for you to decide. Okay, so I'm not going to go through this certainly because we know about the different sources of uncertainty. I'm just pointing out that the spatial scale which climate models are run it's still a part of the climate system response, but particularly with regional models, it can be viewed as an additional source of uncertainty. But what indeed about higher resolution that is not generated statistically? And global models at this point, we're talking about running from about 100, 150 kilometers, 60 to 80 miles, spatial resolution. And one question is, what resolution do we need for adaptation purposes, general or for specific ones? And the important issue here, from my point of view, is how to balance the desire for higher resolution with the other major uncertainties, for emissions, the general response of the climate system, and as we well know now, the internal variability. So here we are. Here is the standard slide I show going from what I call the fuzzy pillow resolution of the western US. And this is with the topography at about 400 kilometers. And certainly this is, much coarser than most global models are running at this point, except for special purposes. 100 kilometers, that's close. Most of the models are running around 150 to 100 kilometers resolution. And you do see now the backbone of the Rocky Mountains. Notice also, when you're going from 400 to 100, you now have Florida. And there is at least one person here who is interested. Oh, and another person. Several people interested in the well-being of Florida. Okay. Now, if we get down to the regional climate model scale, let's say, I'm going to show you some results from 50 kilometers, but now people are going to higher resolutions, for example, 25 kilometers, and here you can really see very clearly distinguish the coastal ranges versus the Rocky Mountains, the basin range area, and so forth. And all these, the Great Lakes are getting sharper and sharper, and the smaller lakes up in Canada are showing up. Now, this is also important from another point of view, and this has to do with working with stakeholders about people's sense of identity with a region. And if you show people results for the western US that look like this, or even this, there's a credibility problem that isn't exactly scientific, but it has to do with whether or not is this region recognizable to them as their region. And so if you're talking to stakeholders or the public, this becomes a very important consideration, which is both a scientific issue and a perceptual issue. All right, to just give you a quick view of how things improve with resolution. Sure, here we're starting off at a 300 kilometer resolution of average annual precip for the western US. Here we're going to 75 kilometers, so this is higher than the resolution at which most global models are currently run for long simulations. I'm talking about, 100, 200 years. And here we're down to 50 kilometers, and you can clearly see that as the resolution increases, you see in more and more of the spatial detail, right? And here is a set of observations at that 50 kilometer resolution. So the general assumption is that, if we get higher and higher resolution, don't things get better? Don't things validate better? Thus, don't they have better information? Thus, shouldn't we just keep doing this until we resolve the resolution of my right large toenail? Or yours. There's probably not that much of a difference. So pulling back to the objectives of downscaling, and this speaks somewhat to what Haley mentioned as well. I put this into two categories. There's the bridging the mismatch of spatial scale between global models and the resolution needed for impacts and adaptation assessments. And this can be done through statistical or dynamical downscaling. And also to resolve high-resolution processes that are responsible for regional climate, so process-level studies. And one of the things I think that's very important to emphasize is that different objectives may require different types of downscaling, because as Haley said, the different methods, it makes a very big difference in terms of both human and computational costs. And one of my big concerns about this whole business is what's a good resource balance to different parts of the climate change problem? Had $1 gazillion, which is a real number, we know. How many of those gazillion dollars would you put into doing very sophisticated regional modeling down to the scale of my large toenail? And how much would you put into looking at, in a much higher resolution, more detail and deeper, about the vulnerability of populations in an urban center? So I'm interested in, I'm going to present this sort of both technically about downscaling, but also how does this fit in terms of, let's say, the integrated uncertainty that we were talking about here.
Could I ask a quick question? Is there a reason you didn't put temporal scale in there as well? Or...
Of course, sure. Temporal scale. That goes without saying, I thought. But now it's been said, hasn't it? But one of the big issues is, but once we have more regional detail, what difference does it really make in any given impacts adaptation assessment? What is the added value of these methods? And I'm talking about dynamical downscaling primarily here. And critical to that is, do we have more confidence in the more detailed results? Because if we can't establish a differential credibility about the high resolution modeling, then one can certainly ask, then why are we doing this for the sake of, if we're talking about impacts and adaptation studies? And we're going to get back to the added value issue later in my presentation. So what really is high-resolution climate modeling, be it a stretched grid system, a very high-resolution global model, although there are problems with that, or a regional model, is that it really does provide insights on realistic climate response to high-resolution forcing, i.e. mountains, coastal ranges. Let's say you want to look at a study about spatial variation of salamanders in the Appalachians. Don't laugh. We're doing that study right now. Yeah. Other things that I'll talk about later, not just mountains, coastlines, and also some very high-resolution atmospheric processes like convection, for example. So the basic regional modeling strategy, it's pretty straightforward. The nesting regional modeling technique. The global model provides the initial conditions, soil moisture, sea surface temperatures, sea ice, and it provides the sea surface temperatures, for example, throughout. And then the lateral meteorological conditions, temperature, pressure, humidity, every, let's say, 6 to 8 hours, although the frequency of providing boundary condition varies. And the global model is supposed to provide sort of that large-scale response to the forcing, let's say on orders of hundreds of kilometers. And then the regional model, driven by the global model, is presumably providing the finer scale, tens of kilometers response. So this is a somewhat old slide, but I have to show it for another reason having to do with Florida. So this is the older version of the Hadley model, the HAD-CM3. Pretty coarse, 2.5 by 3.75. I got this slide from Ray Arrett at Iowa, I think. And I first looked at this, and I saw this, and I thought, what is that? What is that? Is it a golf club? Is it? And I thought, it's Florida. It's Florida escaping from the mainland. Florida has decided to join Cuba, sort of a reverse migration. No. It's actually the Caribbean kind of lumped into this thing. Now, it's interesting that they chose to represent the Caribbean, but not Florida. And I don't know if that was a scientific choice or not. So anyway, so here then is the resolution at 50 kilometers. We have Florida. Again, we have the Great Lakes and so forth. Now, uncertainties. Will they ever end? And the certain answer is no. Regional modeling adds its own. It's not just that the resolution is higher than the global model, but very often the regional model has different physics, dynamics, parameterizations than does the GCM. So you're actually then combining different model characteristics from the GCM to the RCM. Now, some systems, for example, at the Hadley Center, they really try to match that very carefully within the limits of the fact that they're running at different resolutions. The size and location of the domain of interest can have a tremendous effect. The effect of the quality of lateral boundary conditions, i.e. how good are the boundary conditions coming from the GCM. And as colleague in my group, Melissa Bukovsky, has recently just finishing this paper about the North American monsoon, if you have lousy GCM conditions coming in, it doesn't matter what you do to the resolution. You're going to come out with, let me think, what term can I? You're going to come out with garbage. Thank you, a nice clean term. Good. Also, different realizations will produce different climate simulations, i.e. using different realizations of GCM. And as Clara mentioned, we're actually in the process as part of a new program going to use some of those realizations from her newer runs and see what happens when you combine them with regional models. Okay, so I'm going to quickly, oh my, how time passes when you're having a good time. I'm just going to show you very quickly a few slides from a program I've run, which started in 2006, the North American Regional Climate Change Assessment Program. Oh. It's gone. No, oh, sorry. NARCAP. I started the week with a cap. I'm ending the week with a cap. NARCAP. NARCAP. Get it? This is why I do these programs, is to come up with these cute little silly things. I know it's hard to believe, but it's true. Okay. So in this program, we used 4 different global models, which drove 6 different regional models, because that's another problem. Different regional models respond differently. There have been a number of programs like this. The first ones were certainly in Europe, Prudence and Ensembles. Now, through another program, Cordex, there are multiple programs like this. So we were doing, at the time when it started, 2006, resolution about 50 kilometers. And we wanted to develop this also explicitly for use in impacts and adaptation assessments. We did a careful job of evaluating the regional model's performance. It has a cast of thousands with these different entities, and it was funded by multiple US agencies. It was also an international program in that we had people from the UK Hadley Center and also Uranus in Canada. So here's the domain at 50 kilometers. Here's the basic plan. We used only one emission scenario, 4 different GCMs. We only could afford to do 30 years in the current and 30 years in the future. And then these are the 6 different regional models that we used. And I'm just going to show you a couple of spot results on this. So one of the things that we did, and it's interesting that no other program has done this, is we actually created a balanced matrix. Because again, we didn't get enough funding to do the full 4x6 matrix. So we developed this balanced fractional factorial design such that the matrix is sampled in this fairly balanced way. Each GCM provides boundary conditions for 3 different RCMs, and each RCM uses 2 different global models. And that actually makes some of the statistical analysis and process level analysis a lot more robust. I'm not going to have time to go into that, but I just wanted to mention it. Okay, so here we have, here's just a sample result. It's just the change in summer temperature. This is the result from the CCSM3. a large change in the western, kind of midwestern part, northern and midwestern. And then here are the results of 3 different regional climate models, all well tested and well used, or often used, the MM5, WRF, and the Canadian CRCM. And you can see very dramatically how different their responses are. Yes, but that's somewhat damped because, of course, they're receiving boundary conditions from the GCMs. So this is, another source of uncertainty. Which of these are right? Or are they all right? Are they all possible responses? Could we average them? Should we just statistically downscale the CCSM? Do we believe that these answers are better? A lot of this remains really not well explored, which is kind of disappointing. All right, so now I'm just going to show you one major result from this very quickly. And this is looking at the 17 GCMs using the AR4, using the A2 scenario. And this is just the change in summer precip, where we see, a big decrease in precipitation here, somewhat of a decrease there. I'm going to skip this one because it's too hard to explain. But here's the result from these 11 RCMs. And one of the things you see is this great deepening of the decrease in precipitation. Very striking decrease and a greater increase to the north. And so one of the questions about this is, and this is the average, however, and we have to look at them individually, of course, is the higher resolution from all these models giving us new, better information? And how do we establish that? I'm going to show you a quick result from the Central Plains there, just to show you in detail what happens to these models. So what happens, basically, the black figures are the results from the GCMs, and what happens is that the regional models driven by these 4 GCMs tend to all become more negative. And there's this, somewhat of a linear relationship on the change in precipitation and the change in temperature. And right now, Melissa Bukowski and Rachel McCrary are working on teasing out, on a process level, is this better information or not? So the conclusions are what they are. So they are what they are, It's actually all in that paper that I gave you to read. So the problem is, if we think this has more information, so then eventually we're going to come up in this world of the mother of all ensembles. This is also a nice a slide from Ray Arrett, where you have, the future. We have a bunch of different emission scenarios. We have a bunch of different GCMs, plus a bunch of different realizations from the GCMs, different RCMs, and then, yes, we can do different realizations with the RCMs, but that's certainly less important. So, imagine doing all this and driving this, doing double nesting, let's say down to 10 or 5 or 1 kilometer. That's a lot, even though computational resources are increasing at an amazing pace. There's a new program, it's been going on for several years now, the Coordinated Regional Downscaling Experiment, CORDEX, started by Filippo Giorgi and Colin Jones, in which there have been domains created from all the land areas and regional models run on all those areas. And this program is going great guns. At the meeting on this in Brussels about, a year ago, 6 months ago, it was just amazing how much work had been done on this. It's generated a lot of research. I think it's generated some good process level studies, so we're learning more on a science level. How all this will shake out for adaptation assessments remains to be seen. So CORDEX, it's providing a set of regional climate scenarios, making data sets available, generalized framework for testing and applying regional climate models, and importantly, to encourage participation of more scientists. So one of the goals is really to entrain more developing world scientists in this. And one of the things that I appreciate about Cordex is that Africa is in white because that's the central, that was the focus domain for everyone to work on. And I thought that was definitely worthwhile because there just has not been a lot of work on the African continent at even 50 kilometers. And by the way, the basic resolution of Cordex is 50 kilometers. Also, why? When many more sophisticated areas like Europe were going down to 0.11 degree resolutions, it's to make, again, for the sake of developing a robust scientific community within Africa, for people who do not have the resources to be doing 150-year runs at 0.11 degrees. All right, so here are some results. This is just from an earlier program, actually, using the A1B SRES scenario, but with 2 different GCMs. And again, it's all, this is very useful and very good to do. And we see here, I think this is the annual average change. Different GCMs here, the top set, always driven by the ECM5. And we see, again, different directions of precipitation change, increases and decreases. I mean, this is a very standard kind of result that one gets with all of these programs. Here's a result from the Canadian group. The domain is actually all of North America. And I just wanted to show you another feature, let's say a relatively high resolution regional feature. They did 0.44, 0.22, and 0.11. It's nice to compare resolutions to see, are you really getting a lot more? And so here, this is lake effect snow in the winter, in February specifically. And you see it, you actually see it. These are the observations down there. It's a little bland, let's say at 0.44, pretty good at 0.22, and I suppose you could say it's best at 0.11. But the question is this good enough? And will you really get such a different response if your concern is with changes in lake effect snow that it's worth going down to 0.11? I'm not saying it isn't. I just think that these are questions that remain hanging as my time disappears. Okay, going higher and higher. So there's also now a move, indeed, to do process level studies at higher and higher resolution. Obviously, very good, important for convective storms, especially if you actually create convective permitting models, let's say down at 1.5 kilometers. For example, the experiment by Lizzie Kendon and colleagues in Nature Climate Change. Diurnal cycle of convection. Yeah, it's very difficult to get that even out of 50 kilometers, or even as it turns out, 12. Also, urban and land surface feedbacks, and in our cities module, Andy Monahan will be talking about that, where using a high resolution may really get you somewhere that's important to get to. So here's just a quick look at Lizzie's results. It's comparing, they used the Hadley regional model nested in the Hadley global model run at 60 kilometers. They then did 2 different double nesting, one at 12 kilometers with the Hadley regional model and one at 1.5. And the 1.5 one is that it's convective permitting. In other words, you're no longer using a convective parameterization. You're actually resolving convection physically. And these are the results. This is the bias. I'll skip that and just go down to the change. And they did, I think, 13 years in the current period and 13 years at the end of the 21st century. Is that right? Haley was also a co-author on this. And what this shows is the change in heavy precipitation, the top 5th percentile of precipitation events. And here we have 12 kilometers. That's pretty high. You're not going to be doing 12-kilometer runs for 150 years over a large domain unless you've got a lot of computing power. This is just for southern England. But look at the difference in terms of those heavy events with the 1.5 kilometer. And this is, I think, an important result in terms of demonstrating that with a convection resolving model, you really get a different perception of the extremes. And what they say is then we conclude that accurate representation of the local storm dynamics is essential for predicting future change in convective storms, along with accurate representation of changes in the larger scale environment inherited from the driving GCMs. Now, Haley and I had a very interesting little discussion about this right before. And one of the questions is, so are they really saying, well, everything should be done at this resolution? No, it's for predicting future change in convective storms. But you might say that this is a very useful and important process study. But you can't say that you can now use this result for doing adaptation planning. It's too limited. And surely other people will do this and we'll see other results. And this result probably is robust. But that doesn't mean that we now have to run everything at this resolution. But it's a very important result in terms of physical processes. All right, another one is California. I'm going to skip this. Also by Alex Hall, multiple nests down to Los Angeles. There we are. Just for your information, I lived right there during graduate school. Amazing. So to make a long story short, as I run out of time, I just want to say that yes, you really do get more out of these runs. For example, the sea breeze, the resolution of the San Gabriel and these, not very high but important mountains enclosing the basin, you get a very different perception, for example, of what kind of climate change you'll have in Santa Monica, where I lived just a few blocks from the beach. And it's very interesting, the reaction of the press to this. They were all over this. Again, why? This is one model in one GCM. Although Alex did something really smart, he figured out statistical relationships to be able to determine how WRF would respond to other GCMs, which is really a great thing, another great advance. But the LA Times just went wild. Again, why? Why? Because they have maps of how climate change is going to change in Venice versus Ocean Park versus Santa Monica versus Malibu. I'm going back to California. So finally, I think this is kind of finally. Yeah, it is finally. So what about that added value? For one thing, I don't think we really agree about what it is. It's always said, well, if you reduce the bias, you're doing better, right? Because you're reproducing the observations better. Is it related to reducing uncertainty? Is it related to characterizing uncertainty? Is it just have to do with a more general thing of having greater regional knowledge? Or is the added value more in the co-development of scenarios, with stakeholders? Do we agree on how to demonstrate it? We do not. I think both Hall and Candid showed some added value, but the thing is, but what do you do with that? Because it's in such a limited context. And with that, the other problem is that we haven't done a very good job in terms of comparing these different methods. This is from the National Academy Study on Advancing Climate Modeling. We need more systematic evaluation and comparison of the various downscaling methods, because until we've done a good job with that, we're kind of back to touching the elephant with a bunch of blind men to sort of tie it all together. I won't read this. I'll just say that there are really different perspectives. Climate scientists tend to believe we need a lot of great deal of detail to do adaptation studies. People more in the social science and, in this case, human design say effective and robust adaptation strategies are not significantly limited by lack of accurate and precise regional climate predictions. And I think we're still really kind of battling over that. And that's the end.
Thank you.
Thank you.
Did we thank Haley too? I can't remember.
We did.
Okay.
But we can thank her again.